Hi everybody, welcome back to my channel on Feynman integration. This is going to be a really easy and quick video. I'm doing this one just to show you that although Feynman integration is usually used to solve integrals that can't be solved any other way, it can also be a quicker way to solve some integrals that could be solved using traditional methods like integration by parts. Specifically this integral here, the integral from 0 to 1 of x to the 5/3 times the natural log of x dx. If you saw that one on like a Calc 2 test, or you would, it's integration by parts. That's what you would do. But it can be done a little bit quicker. In my opinion, a little bit nicer using Feynman integration. So the first thing we're going to do is we're going to create a function of t, and we're going to label it big F of t. And it's going to be the integral from 0 to 1 of x to the t dx. And sometimes with Feynman integration, it can be a little bit difficult to figure out the steps, which is why I think it's not taught very often. It's more, there's a little bit more like creativity involved in it instead of just a step-by-step process. You kind of have to use your imagination a little bit. But in any way, you can see why I chose x to the t is because when you take a derivative of x to the t with respect to t, you'll recover that ln x right there. So anyway, we have big F of t is equal to the integral from 0 to 1 of x to the t dx. And you could easily evaluate that to 1 over t plus 1. So our next step is to use the Leibniz rule to get to little f of t. And if we use the Leibniz rule on this, we take a derivative with respect to t of the entire function by taking a partial with respect to t of the integrand. And what you get if you do that is this. You'll get that little f of t is equal to the integral from 0 to 1 of x to the t ln x dx. And that's almost the same as this, except we have a t instead of the 5/3. So now what we do, if we want to find what this is equal to, well, we know that it's equal to the derivative of this, which so all we need to do is take a derivative of this to find what this is equal to. And we find that it's equal to -1 over t plus 1 all squared. So there we have an expression for f of t, and you notice, like I said before, that it looks almost the same as this, except we have a t there instead of a 5/3. So now literally all that's left to do is to plug in 5/3 into our function of t, and then we'll get the answer. And so yes, you see I is equal to f of 5/3, which is equal to -1 over 5/3 plus 1 all squared. And that evaluates to -9 over 64. So that's the answer. And you can verify that using integration by parts if you'd like. But I just thought this was a nice quick video that I could kind of do on the fly since I hadn't posted one in a while, just to show that, well, Feynman integration is usually used as a substitute for things like contour integration. It doesn't have to be. You can use it as a substitution for some easier integrals too, such as this one. And I might do a few more examples of Feynman integration being used to solve simpler integrals. But anyway, that's it. I hope you enjoyed that.